Gather round, eager mathematicians. Let me tell you a story about rotations in 3D. This is a great little thing that's come over from Reddit. Again, I'm trying to go through some of these at the moment. We have this 3x3 matrix, got a little 1 over k in front of it, but we are told it represents a rotation in 3 dimensions. Whew. First job is show that k is 1 over 49. Well, what we do know about this, so let's go up here. If it's a rotation, it preserves volumes. And if it preserves volumes, that means that the det of m has to be 1. Now we can find the determinant of this thing here. The determinant of this 3x3 matrix, I'm not going to fill it all in. Now you can sit down and work it out by hand, or we can go to our good friend Le Calculator, and that will tell us that the determinant of that thing is in fact 49. So that tells me that the determinant of m is 49 over k, which has to equal 1. Therefore, k is 49. Simples. Okay. Now, let's find the axis of rotation. Now, the axis of rotation is an invariant, well, it's a line of invariant points, right? If you are on the axis of rotation, you will not rotate. So we want to find those points that do not rotate. Okay. Now, I don't really want to deal with this, but there we go. So what this tells me is that 36, 4, 33, 32, 9 minus 36, minus 9, 48, 4. That will equal to 49 times x, y, z. If we are on, if we are an invariant point with coordinates x, y, z, if we are an invariant point with coordinates x, y, z, all I've done is, to avoid having a bunch of fractions here, I've taken that 1 over 49 and I've moved it over to the other side. It's a scalar, we can do that. So that's going to give me a bunch of really cool equations that, if I tidy up, is going to be minus 13x plus 4y plus 33z is 0. It'll give me 32x 9 minus 40y minus 36z is 0. And it'll give me minus 9x plus 48y minus 45z is 0. Now, obviously, there are infinitely many points. So these are all combinations of each other. So my goal is to just get an equation for x in terms of y, x in terms of z, and we will go from there. So can I cancel out the y's? Yes, I can. If I do 10 times equation 1 plus equation 2, what does that give me? If I do 10 times equation 1 plus equation 2, so that's minus 130 plus 32 is minus 98x. That goes away, and it's 330 minus 36 is 294. Z is 0. Ooh, that looks good. 294 divided by 98. Ooh, that tells me that x is 3z, so that's nice. Now let's try and get rid of the z's. Okay, 36 and 45. That's 4 times 9. That's 5 times 9. So if I go 5 2's minus 4 3's. 5 2's minus 4 3's. So 5 times 32 plus 4 times 9. That's 196x. 5 2's minus 200 minus 4 times 48. Minus 200 minus 4 times 48 is minus 392. That also looks quite good. What's 3? Yeah, that's twice, right? So x is equal to 2y. So in fact, right, the equation of the axis of rotation would be x is equal to 2y is equal to 3z. But let's write this in slightly better form. Divide everything by 6. Because now that tells me, right, so let's write down number 2 here. It tells me that it is in vector form, it is lambda times 6, 3, 2. And that's going to be important for us in a second. Okay? So that form there gives me my direction vector. And I'm going to need the board. So that gives me the direction vector. Nice. Nice, 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 nice. Right, invariant points. Invariant planes. Now, what planes are going to stay invariant? So the points will rotate, but the plane doesn't change. Well, they are planes that are perpendicular to that guy. So I want planes where the normal vector is 6, 3, 2, i.e. a plane in the form 6x plus 3y plus 2z is equal to something, right? They can be all parallel to each other. But that's the idea. If you are an invariant plane, you are perpendicular to the axis of rotation, right? A stick with a sheet of paper. So that one's nice and easy. Now let's find the angle of rotation. The easiest way to do this, right? The easiest way to do this is to just see where a point goes. So let's just pick a point. Let's pick a point. And because of that one there, because of that 1 over k, I would pick any point of the form 4900 or 0490 or 0049. Okay, that's probably our easiest bet. So let's transform it. That's 1 over 49 times 36, 4, 33, 32, 9 minus 36, minus 9, 48, and 4. And so I've got to multiply that by the point 4900. The reason for that is, of course, that 49 and that 49, basically we're doing it with the 100 on this one, which gives me 36, 32, and minus 9. Okay. So what have we got? Let's see. We've got our axis of symmetry, and we've got our original point here. Okay? So what we'd quite like, and we've got our transformed point over here. Now let's visualize this all as being in a plane. Now what we would quite like, really, to find the angle of rotation is to find the angle between the lines. Now this line here is in this plane, so it's perpendicular to the axis of rotation. That one there and the point of rotation. So what I'd quite like to find, actually, is where that point is. So I'd quite like to find that point, then I can just play around with that. So how should I find that? Well, we've just said that these planes will be of this form. Well, let's find the equation of this plane. Well, it goes to the point 4900, so that is 6 times 49 plus 0 equals d. So this is the point, the plane 6x plus 2y, 3y even, plus 2z is 6 times 49, which is 300, which is 294. Now we need that to go through this line. So x is 6 lambda, y is 3 lambda, z is 2 lambda. So that gives me lambda is 6. Lambda is 6. So we've got this point here, which was 36, 32 minus 9. We've got our original point, which is 4900. And we've got this new point here with lambda is 6, which is 36. I'm doing position vectors, 18 and 12. Okay? Right. So let's find our two vectors. The first vector between these two things is going to be, you go from 36 to 36, which is 0, 18 to 32, which is 14, 12 to minus 9, which is minus 21. The other vector is we're going from 36 to 49, which is 13, 18 to 0, which is minus 18, and then 12 to 0, which is minus 12. Now, obviously, to find, and now we just want the angle between these two vectors. So let's take the dot product. What does that get me? The dot product is 0, 14 times 18. It's minus 252, which is the minus. And then 21 times 12. Oh! I thought there was a whole load more to do. Bosh, these two vectors have a dot product of 0. They are perpendicular. The angle is pi over 2. Isn't that wicked? And I know normally when we're doing further maths A level, for example, we only really deal with rotations around single axes, but this is a really cool illustration of how you can have a more general one and figure out what that rotation is if it is a rotation. And that's really, really cool. I enjoyed that. I enjoyed that a lot. Don't forget to subscribe, like, drop a comment. Did I miss anything? Would you have done it differently? Let me know. Hit the bell for notifications as more of these come out. I'm Nick. This was some really, really cool maths, and I will see you next time.